Okay, second transformation of the week. Well, fourth if you're doing the other two as well, but this is the second one I'm going to explain to you. It's enlargements. Common error here is that you forget that we're doing maths and use enlargement as a normal English word when it has a technical meaning in maths as well. Enlargement means change of size or related by similarity. It's not just getting bigger. Sometimes it is, but sometimes it also includes getting smaller, and that was later another weird effect as well is related to it. So, single transformation that maps A onto A prime. We can see those two shapes are not the same size and they are similar to each other. They are mathematically similar, so it must be an enlargement. So it's an enlargement, mark 1. But just to say that this change size doesn't tell you exactly how to get this shape to become that shape. We must know how much it's got bigger. There must be some way of describing that, and we must have someone describing exactly where it ends up, because it didn't end up down here or over here. It ended up here in the corner. So, to do that, we need to find the centre of enlargement, which is like a projection. Like at the cinema or in the classroom, you have a point source of light, which gets larger the further away you get from it until it's big enough to fill the screen. If something gets closer to the centre, it grows. Further away, it will change the proportion. And in fact, I should have done that with a projector. It's the opposite with a camera. The scaling is inverse. So, find the centre. So this vertex here came from this vertex here, and we shall just join them, because projections are like light; they go in rays and straight edges. This edge came from this edge, so we shall join them. This edge came from this edge, so we shall join them. And this edge came from this edge, so we shall join them. And you can see all of these come from the same point. Now, unfortunately, I managed to pick a point that isn't an integer, which means I must have made a mistake when setting up the question. I'm sorry about that. So these all join at the same place. So we're going to use that in our sentence. A to A prime is an enlargement by a scale factor of. Now, scale is just a word to do with size. Factor, as you know, is to do with multiplying and dividing. So we'll have to multiply this by to get that. Well, that is 1 tall, and that is 3 tall. 3 divided by 1 is 3. This is 2 wide, this is 6 wide. 6 divided by 2 is 3. So it's a scale factor of 3 from here, which looks like it's 5.9 negative 8.3, which is unhelpful, but I'm sorry about that, that was my error. So the coordinate is 5.9 negative 8.3. And that point there is the point it all came from. I'm going to show you one more effect here, which is really quite important about where this ended up. If I measure from this vertex to the centre, we will get a measurement, which looks like it's 3.9 centimetres. So this vertex here is 3.9 centimetres away from the centre enlargement. The same vertex on the image is 11.7, go on, 11.8, 11.7, it's 11.7. If I divide those, you'll also get 3. So it's not just 3 times larger, it's also 3 times further away, and that's how we get the location correct as well. So you need to get the type, which is enlargement, the multiplication, which in this case is 3, and the place it all started, which in this case is this coordinate over here, this decimal. Alright, I've got a few more examples of how this can get a bit weird. So similar idea, B to B prime. Clearly it's change size, clearly it's enlargement. Let's find the centre. So the centre from there to there, there to there, there to there. I missed a bit. Yeah. So, slight inaccuracy here in my rays. I missed this vertex, which means that one of these edges is wrong, but there's a point there. That's the centre, and that is 4, 7. So it's an enlargement from 4, 7. The tricky thing here is the scale factor. So this is 2 units tall and this is 5 units tall. You've got to be careful about which way around you do the division. We always had prime divided by not prime. We had the image divided by the object. So 3 over 1 and 6 over 2 was result over original, or image would be more normal over object. Just like with proportional growth. So here, because that has the prime, that is the image. So the division is 2 divided by 5, which I would just write as 2/5. Okay? Now this fraction is less than 1, which means this is less than the whole size of this. And less than the whole means smaller. So this is an enlargement getting smaller. We turned this larger triangle into this triangle by multiplying by 2/5. And any measurement, this is 2.5 divided by, this is 1. So that's 1 divided by 2.5, which is also 2/5. And we can do the same thing with the hypotenuse. And the lengths rule applies as well. So this all works the same way, just when it gets smaller, it gets nearer to the centre. Then the weird one! What's happened here? It's changed size, it must be an enlargement, but it's not the same way around. How could that happen? Well, you need to pay attention to exactly which vertex is which. So here, it was obvious that that vertex was that vertex, because this has got no symmetry, we can't get them mixed up. However, here, there was lots of symmetry. It wasn't really obvious that that right angle was any different from any of these 4. It worked out that way. So if we label these vertices as P, Q and R, I happen to know that that would have been P prime, and that would be Q prime, and that would be R prime. And that means that when we do our edge joining, our vertex joining with our rays, we in fact get something sensible. They meet there, which is kind of cool. So clearly this is twice the size of that, twice the width, twice the height, all the length are doubled, so there's clearly a 2 involved for its scale factor, but it's not quite right. So this has got 4 squares up. If I double that, I should end up over here somewhere, 8 squares up. Okay, but I don't, I end up 8 squares down, which is backwards. So the scale factor here is -2. It's gone back 2, which is how it's got squashed inside out. It's come back through the middle and spat out backwards. Okay, and that's the weirdest enlargement. Now we can combine these. We can do fractions which are negative, we can do fractions which are positive, and we can do any of the previous things we've seen to be mixed together in any way. So that's how you describe them. Now what about doing them? So we've got 2 examples on the same page to save some space. We're going to enlarge D by a scale factor of 4 from the 0.77. So first job, find the 0.77. Well, 7 right, 7 up, that is there. Scale factor of 4 means 4 times larger and 4 times further away. There are a few different ways to do this. I would draw the rays whichever way I'm doing, just as a guide. So from this point through, these vertices will be that direction. And this corner will head off in this corner, this vertex, what am I talking about, will head off in this direction. Try and be kind of accurate. And this other vertex will head off in that direction, which is there, I think. Now, this has been done by hand and by eye, and a tiny error here only grows as you get over here. So this could be an entire square out, based on how accurate I've been here. Okay? So don't follow this too accurately. You've got to do some other maths to check it's the right place, but it gives you an idea that that's going in that direction. I would normally here count squares and count distances. So this gap here is 2 squares. Scale factor of 4. So I need to do, this gap needs to become 8 squares. So 1, 2, 3, 4, 5, 6, 7, 8. That gets me there, because 2 times 4 gets me the 8. And that means this point here is the corner, is the top right vertex. This gap here is 3 squares away. Times that by 4, we get 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At this point you've got a few choices. You can carry on doing that method to get all the vertices, or you can realise that you know enough maths to work out the rest of the shape. Because it's a scale factor of 4, every length here is 4 times as long. And look, those are already 4 squares apart compared to the 1 square apart here. The height of 1 becomes a height of 4. If I go 4 squares down, oh look, I'm on the line, I'm on the ray again, which means I'm pretty accurate. If I go 4 squares down, brilliant, I'm on the ray again. So that guide has helped me. It means I was reassured that when I counted 4 squares it was lined up, I didn't make a complete error. If I ended up some way away from the ray, I'd have to check which one was wrong. But because they both get me a similar thing, I've got a pretty good idea that I'm right. So this will be D prime. Let's just get that a bit thick around the edges so you can see it. So that is D prime. It's 4 times further away from this point than D, and it's 4 times taller, 4 times wider, 4 times longer in the diagonal. It's 4 times longer. Right, E, I've put a tricky one in, scale factor of a negative third, just because I'm feeling mean. So the coordinate is 2, 0, which is there. I'm going to use our rays again. I'm going to just use this point first to think this through. So that would be our normal ray. A third of the distance would be here. But it's a negative third, so it's going to be that distance backwards. So that is 3 diagonals, or 3 root 2s if you're keeping track of the Pythagoras going on here. But it's 3 hops, 3 little hops to make that length. A third of that is 1, but it's 1 backwards, so it's going to end up in this direction, over there. This is going to end up over there somewhere. Now, it's going to be the same height as that, so it should be there. And we can start to see what shape this is going to be. So that is a third of the height, a third of the width, all the lengths have been multiplied by a third, but it's backwards and upside down. Is it in the right place? Well, I've only actually checked two vertices, so I might be wrong. So let's just double check that if I join up to the other one, it does go through the centre. That's pretty good. So that is how we perform enlargements, even if they're weird ones. I hope you have fun with this topic. It gets pretty fun in 3D as well, and it's pretty useful for optics and other projection-based bits of maths. Have fun!